Welcome back to this deep dive. We're continuing our journey through the CPMAI version 7 framework today. And if you've been following along with our previous discussions, we've already tackled phase 1 where we really nailed down our business problem, and then phase 2, which was, all about just understanding our data.
Right. Phase two is very much about data understanding, doing the inventory, running quality checks, looking into legal rights. It was a very investigative phase.
Exactly. It felt a bit like we were detectives, right? Dusting for fingerprints and reading the fine print just to see what we actually had sitting in the warehouse. But today feels different. Today we are rolling up our sleeves and moving out of the planning stages. We're getting our hands dirty with phase 3 data preparation.
Yes, and I really get the sense that for a lot of project managers and teams, this is where the rubber finally meets the road.
It absolutely is. It's
Right.
this pivotal moment in the life cycle. Because up until now, we've mostly just been looking at the data. We haven't really changed it.
That is the key shift right there. It's the shift from what to how.
Mm.
In phase two, we ask, what is available and is it good enough? But now in phase three, the focus shifts entirely to action. We are transforming that raw material into a specific data set that is ready for modeling operations.
Which is basically fuel for the engine.
Exactly. It's the fuel. And I want to be very clear about this definition up front because it is surprisingly easy to gloss over. Phase three focuses on the activities needed to construct the data set specifically for modeling.
So wait, it's not just a technical step then? It's not just an IT ticket where you say, hey, clean this up for me. It's a distinct phase of the project management lifecycle.
Precisely. And that distinction matters a lot. If you treat data preparation as just some background technical task, you lose critical oversight. This phase takes the data we verified in phase two, and it scopes it, cleans it, enhances it, and crucially labels it.
Scopes, cleans, enhances, labels. I mean, that sounds like a ton of work.
Yeah, it is the blue-collar work of AI. Honestly, it's the heavy lifting. Think of it this way. If phase two was drawing the architectural blueprint and, inspecting the lumber yard to make sure the wood wasn't rotten, phase three is actually cutting that wood to size. It's planing it and sanding it down so it fits the frame of the house.
Because you can have the absolute best blueprint in the world, but if your 2x4s are warped or cut to the wrong length, your house is going to fall down.
Exactly. You can't build a house with raw logs, and you cannot build a cognitive model with raw data dumps.
That makes total sense. So, looking at our roadmap for today's deep dive, we have 3 specific task groups to cover. And I see we actually have some priority ratings attached to them in the framework, which is super helpful for figuring out where we should focus our energy.
We do. And the roadmap is highly logical. It follows the natural flow of the data itself. We start with task group 1, data selection, which is rated high priority. Then we move to task group 2, data cleansing and enhancement, which is also high priority. And finally, we hit the really heavy hitter, task group 3, data labeling.
And that one is rated critical priority, right?
Yes, critical priority.
Critical is a strong word. We don't throw that around lightly in the CPMA framework.
We definitely don't. And we will get into exactly why labeling is so unique to AI a bit later. But the short version is that while selection and cleaning happen in pretty much all traditional software projects, you always need to clean up your database. Labeling is incredibly AI specific.
Right, because it effectively constrains what the system can learn.
Exactly. It constrains it in a way that rule-based software never requires.
Yeah.
If you mess up the labeling, you haven't just introduced a bug, you've taught the machine the wrong reality.
Wow. Okay, so the stakes are definitely high. And the overall goal, by the time we finish this deep dive, is to understand how we get to a data set that is fully ready for phase 4 model development.
That is the mission. Clean, relevant, and trustworthy data by the end of this phase.
All right, let's just jump right into the first bucket then. Task group 1, data selection. High priority. Now, when I see select data, my immediate first thought is, okay, just download everything we have. I got a massive hard drive. Let's fill it up. More data is always better for AI, right? But I had a sneaking suspicion you're going to tell me that's a terrible idea.
It is a terrible idea, and honestly, it is one of the most common early mistakes organizations make. Select data isn't just a massive data dump. It is a formal, deliberate decision-making process. You aren't just grabbing files. You are determining exactly which specific data sets and which specific records within those data sets are going to be allowed into your project.
Why does it need to be a formal task, though? Why can't I just grab it all now and let the data scientists sort it out later?
Because of the rationale. The framework emphasizes this heavily. It is not enough to just include data. You have to document why you included it. And honestly, perhaps even more importantly, you have to document why you excluded other data.
Oh, interesting. So if I deliberately leave something out, I actually have to write a note explaining why I didn't want it.
You absolutely have to. Think about the long-term accountability here. Let's look at a concrete example to make this real for you. Imagine you're managing an AI project designed to predict customer churn. You want to know who is about to cancel their subscription so you can, send them a coupon or give them a retention call.
Sure, classic use case. Everyone wants to stop churn. It saves the company money.
Right. So you look at your company databases. Let's say you have 20 years of customer data sitting there, but you decide to only include the last 24 months of data for the model to learn from.
That seems totally reasonable to me. I mean, the market changes, buyer behavior changes. Data from 2 decades ago probably doesn't predict how someone is going to act in 2026.
Exactly. That is your rationale. So you document it. You write down included last 24 months because it is representative of current behavior patterns. But let's say there is also a legacy database sitting there from a smaller company you acquired about 5 years ago. It has customer data, but the schema is totally different. It's messy. It doesn't link up well with your current CRM system, so you just decide to leave it out.
Okay, that also makes practical sense. It's incompatible. It would probably take way too long to fix, and maybe our project has a really tight deadline.
Correct, but here is the absolute key. You must write that down before you start cleaning anything. You write, excluded legacy records due to incompatible schema and linkage risk. If you do not document that, you open yourself up to a massive accountability risk later on.
What's the risk? Is it just that the team might forget why we did it?
It's the accountability gap. Let's fast forward. Say you build the model, and 6 months later, it is failing miserably for that specific segment of customers that originally came from the acquisition. Maybe those customers behave a bit differently, and your model never learned their specific patterns. So your stakeholders come to you, angry stakeholders, and they say, why is the model broken for these people? Why didn't you train the AI on them?
And if I didn't document my decision back in phase 3?
You are standing there shrugging your shoulders. You look completely incompetent. You can't prove if it was just a data availability issue, a technical oversight, or a deliberate strategic choice.
Yeah.
You have a reproducibility failure and an explainability failure on your hands.
But if I have this documentation, I can pull it up and say, look, we made a conscious, agreed-upon decision to exclude that group because the data structure was incompatible. We flagged this risk in phase 3.
Exactly. You can say, if you want us to support that demographic now, we need a separate spin-off project to fix that legacy data first.
I see. So it turns what looks like a failure into a properly scoped business decision. It shifts the conversation from, hey, you messed up, to, hey, we decided this together based on these constraints.
Exactly. It protects the project and it protects the team. This is the big difference between just grabbing whatever looks useful and executing professional data selection. It creates that vital audit trail.
Now, there is a distinction here that I think trips up a lot of people when they're first learning this framework. We're talking about data selection right now, but later in the project, in phase 3, there is something called feature selection.
Yes. This is a classic trap. It is a huge stumbling block.
Because it sounds like the exact same thing to a layperson. I'm selecting data, aren't I? Whether I'm picking tables or columns, isn't it all just picking stuff?
Ideally, yes, it sounds similar. But technically, within the framework, mixing them up is a fatal error. Here is the task discriminator you need to keep firmly in your head. Data selection, which we are doing right now in phase 3, is about the rows. It is about the records. Which sources and which individual records are we letting into the room?
Okay, and feature selection.
Feature selection, which happens in phase 4, is about the columns. It is about the variables.
Okay, let me try to play that back with an analogy to make sure I've really got it. Data selection is deciding we are using the customer database, but only the customers from the last 2 years. That's selecting the rows. I'm choosing exactly who gets to be in the data set. I'm acting like the bouncer at a nightclub. I decide who gets in the door.
I love that. Yes, you are the bouncer.
Okay, and then feature selection is what?
Feature selection is looking at the people who are already inside the club, the records you selected, and deciding which of their attributes actually matter for our problem. So you say, we are going to use the age column and the total spend column, but we are going to completely ignore the favorite color column because knowing their favorite color doesn't help us predict if they will churn.
Perfect. So feature selection is about determining which variables are predictive. Data selection is about the raw scope of the data set itself.
Exactly. Do not conflate the two. Phase 3 is about getting the right records into the workshop. Phase 4 is deciding which specific parts of those records we actually use for the math. If you try to do feature selection right now in Phase 3, you're getting way ahead of yourself. You first need to make sure you have the right records in the building to begin with.
That is a crystal clear distinction. Rows versus columns. The bouncer at the door versus, I don't know, the casting director inside picking the best trades.
Sure, let's go with the casting director.
All right, let's move along to the next bucket. We have selected our data. We've documented exactly why we have these specific rows. Now we enter task group 2, data cleansing and enhancement. This is also rated high priority. First up is the task, clean data. Now, again, I'm going to play the devil's advocate here. Isn't this just standard run-of-the-mill database maintenance? Like making sure the dates are in the right format, fixing typos, making sure there aren't any weird special characters. I feel like I do this in Excel every single week.
It definitely includes that, but for AI projects, the bar is significantly higher. The real goal here is what we call AI suitability. In traditional software or standard business intelligence dashboards, clean usually just means structurally correct. It doesn't crash the SQL database, valid dates, no text string sitting in number fields. If the column says price, it has a $ and a number. That is clean in the traditional sense.
Right. If the system loads it without throwing an error, it's good to go.
But for AI, clean actually means fit for the cognitive purpose. You have to ask a deeper question. Does this data honestly and accurately reflect reality?
Fit for the cognitive purpose. That sounds a bit high-minded. What does that actually look like in practice? Let's get a scenario going.
Let's look at a really common failure mode. Imagine a predictive maintenance project on a factory floor. You have all these sensors on the factory machines measuring temperature and vibration. Your team runs a standard cleaning script. You fix the date and time formats. You remove some duplicate rows. The data looks technically perfect. Absolutely zero errors when you load it into your Python environment.
Okay, so far so good. The IT guys are happy.
But you missed something crucial about the real world. There is a column for a vibration sensor B. And for one very specific type of old machine on the floor, that sensor returns a null or a blank value whenever the machine is sitting idle. It is not an error code. It's just how that legacy system logs the off state. It saves memory space by writing nothing at all.
Oh, okay. That sounds exactly like typical legacy system behavior, just leaving it blank.
Right. But if your data prep team just treats that as a standard missing value, or if they just run a script that replaces all nulls with a 0, because that's a very standard cleaning step.
Wait, if you replace it with a 0, the model thinks the vibration is 0.
Exactly. If the model sees 0 vibration, it implies the machine is running perfectly, incredibly smoothly. But actually, the machine is just turned off.
Ah, I see. So to the model, turned off and perfectly smooth running look exactly the same if we aren't careful with how we clean.
Exactly. So the model learns that 0 vibration means healthy. Later on, when the machine is actually running and happens to have very low vibration, the model might get confused. Or what if you decided to just delete those null rows entirely because you thought they were broken records? Then the model literally never learns what idle looks like. It fails to predict failures on that specific equipment type because the training data was heavily biased by how you handled those systematic nulls.
So the data was clean in terms of the code. It was all valid numbers, but it was incredibly dirty in terms of its real-world meaning.
Exactly. The core objective of cleaning in Phase 3 is leakage prevention, consistency, and correctness within the selected data. You have to deeply understand what the data means, not just how it's formatted. You need to know that null actually means idle in this specific context and handle it appropriately, maybe by creating a brand new column called isMachineOn.
That requires really deep domain knowledge. You can't just automate that away with a script without thinking about the context.
You cannot, and that's why project managers need to facilitate conversations between the data scientists and the domain experts.
That brings us perfectly to the second part of this group: enhance and augment data. Now, to be honest, these two words sound like complete synonyms to me. Enhance, augment, make it bigger, make it better. Is there a real, tangible difference in the CP/M AI dictionary?
There is a very sharp technical difference in this framework, and you need to know it. Enhance is about improving the existing data you already have. Think of it as filling in the potholes on a road. Maybe you have 1,000 customer records, but half of them are missing their zip codes. So you go out and use a third-party postal service API to look up the addresses and fill in those missing zip codes.
Okay, so I am taking the exact rows I already have and just making them richer. more complete.
Right. You are polishing what you currently possess. That is enhancement. Augment, on the other hand, is fundamentally different. Augment means generating or adding entirely new data to address specific coverage gaps. You are actually creating data points that literally did not exist before.
Creating data. Wait, isn't that essentially cheating? If I'm just making up data, isn't that fake news for the AI?
Not if you do it scientifically. In fact, this is incredibly common in AI, especially in deep learning and computer vision. Let's look at the rare manufacturing defects example. This is a classic case where augmentation literally saves the day.
Okay, lay it on me.
Say you are building a computer vision system to spot tiny hairline cracks in airplane engine parts as they come off the assembly line. You have 10,000 high-resolution images of perfectly normal, healthy parts. But you only have 50 images of cracked parts. Because, hopefully your manufacturing process is pretty darn good.
Right, it's really hard to find the bad ones. And you obviously don't want to purposefully break expensive engine parts just to take pictures of them for the AI.
Exactly. But here's the problem. You cannot train a sophisticated neural network on just 50 images. It's nowhere near enough. The model will just memorize those 50 specific pictures, and it won't be able to recognize a slightly different new crack. So what do? You use data augmentation.
How does that work?
You take those 50 images of cracks and you mathematically transform them. You rotate the image 5 degrees to the left, you flip it horizontally, you change the lighting contrast a little bit, you zoom in 10%.
So you basically turn one photo of a crack into 10 slightly different photos of that exact same crack.
Exactly. You are synthesizing new training samples that mathematically preserve the core characteristics of the defect. The crack is still visibly there, but they look different enough to the computer's pixel grid to count as brand new examples. That is augmentation. You are actively solving a coverage gap by generating synthetic data based on real parameters.
That is fascinating. So instead of waiting 5 years for the factory to accidentally produce enough broken parts to train the AI, we just simulate them based on the few we already have.
Correct. It makes the model far more robust.
Yeah.
It essentially teaches the model, hey, a crack is still a crack even if it's upside down, or if the factory lighting is a bit dim today.
And I feel like there is always a huge, but when we get to the cool stuff, there must be a risk here.
There is a massive risk. Whenever you start heavily manipulating data like this, whether it's enhancing, augmenting, or transforming, we have to talk about the governing principle of data leakage.
Okay, let's unpack that term. I hear data leakage, and my mind immediately goes to a plumbing disaster. Or maybe like corporate espionage, where someone is stealing our customer list. What exactly is data leakage in the context of AI prep?
It's actually a bit closer to the espionage idea, just internal to your model. Leakage is when information from the future leaks into the past. Or, to be much more technically specific, it's when information from your test set leaks into your training set.
Okay, remind me why that's bad.
Because the golden rule of AI is this. You must evaluate your model on data it has absolutely never seen before. That is the only way to know if it actually works in the real world.
Right. It's like school. If I give you the answer key to the final exam before you take it, you're going to get an A+. But you didn't actually learn algebra. You just memorized the answer key.
Exactly. Now, consider augmentation or enhancement. Let's say you decide to normalize your data. That's a very common preparation step, where you scale all your numerical values so they sit nicely between 0 and 1. To do that math, you need to know the absolute maximum value in the entire data set, right? So you know what to set the 1 as.
Right. You need the top of the scale to do the division.
If you take your entire data set, all 100% of it, including the data you plan to set aside to test the model on later, and you find the maximum value across the whole thing, and then scale everything based on that, you have just used information from the test set to change the training set.
Oh, I see. Because the test set helped define the scale for the training set.
Yes. The training set has now been subtly influenced by the test set. It knows something about the global range of data that it shouldn't logically know yet. This is a very subtle form of leakage, but it absolutely ruins your evaluation integrity. Your model will perform slightly better during training because it has a mathematical hint about the test data.
Do you have another example? Maybe something more business-focused.
Sure, let's talk rolling averages. Suppose you are predicting daily stock prices or crypto prices. You want to create a new enhanced feature that represents the average price of the last 7 days. If you calculate that rolling average across the whole data set before you split it into your training pile and your testing pile,
Give me a guess. It overlaps.
it overlaps. Let's say your split is at day 100. If you calculate a 7-day average on day 99, and the calculation script accidentally includes data from day 100, day 101, day 102,
You are literally looking into the future.
you are cheating. You are using next week's prices to predict today's price. And the result is a model that looks completely amazing in the lab. It might show 99% accuracy, but it will fail completely and embarrassingly in the real world. Because in the real world, you don't know next week's price yet.
So the big takeaway for phase 3 here is that you generally need to split your data before you apply these heavy transformations. Or you need to be extremely meticulously careful that your calculations purely rely on the statistics of the training data alone. You cannot apply transformations globally if they introduce any information from the test set.
Timing is everything in data prep. It's not just the math, it's the sequence of the math.
All right, to everyone listening, take a breath. We have officially selected our data, rows, not columns. We have cleaned it, checking for actual meaning, not just typos. We have augmented it by creating new synthetic samples while being super careful not to leak the answers to the test. Now we finally arrive at the absolute summit of phase 3, task group 3, data labeling. And this one is rated critical, not high, critical.
This is the heartbeat of supervised learning. If you only remember one single thing from our deep dive today, let it be this section on labeling.
Why does this get the critical label,
Yeah.
no pun intended? Why is this fundamentally more important than, say, cleaning the data properly?
It gets the critical rating because it is entirely unique to AI and its impact. Let's contrast it. In traditional coding, let's say you're building a standard website or a banking app, the human software engineers write the logic. You write explicit code that says, if the bank balance is less than 0, then charge a $30 overdraft fee. You tell the computer the exact rules of the universe.
Right. I'm the lawmaker. I write the rule. The computer blindly obeys.
Exactly. But in supervised machine learning, you do not write the logic. The model learns the logic all by itself by looking at thousands of examples. And where do those examples come from? They come exclusively from the labels. If you show a computer vision model a picture of a cat, but you accidentally label it dog, the model mathematically learns that dog means pointy ears and whiskers. It doesn't know any better. It has zero common sense. The labels are the only reality the model has access to. We call this the ground truth.
Ground truth. I love that term. It sounds almost philosophical.
It really is. If the ground truth is flawed, the model is inherently flawed. It doesn't matter if you have the most powerful supercomputer on the planet or the most advanced neural network algorithm ever published. If your labels are garbage, your output is garbage. You cannot code your way out of bad labels.
So let's talk about the actual task itself. Label data. Is it really just, is it just sitting there and going through and tagging things? Cat, dog, cat, dog?
That is the physical manual act of it, yes.
Yeah.
But the formal task of labeling in the CPMAI framework is about setting up the rigorous infrastructure to do that manual work correctly. You absolutely cannot just start randomly tagging things. That is a recipe for total disaster. You need 3 distinct things defined before you tag a single record. 1, a schema, 2, criteria, and 3, consistency controls.
Okay, walk me through those one by one. What is a schema in this labeling context?
The schema is simply the list of available options. What are the allowed categories? Let's take a natural language project like sentiment analysis. You want an AI to read incoming customer reviews and flag if they are happy or sad. Your schema might be very simple, positive, negative, neutral. Or if it's a more nuanced project, it might be complex. Positive, negative, neutral, mixed, sarcastic, angry, disappointed. You have to lock in those buckets before anyone starts working.
Okay, that seems straightforward enough. Positive, negative, neutral, boom, done.
But then you desperately need step 2, criteria. These are the written definitions for the schema. Because let me ask you this. If a customer runs a review that says, the product is great, but the shipping was incredibly slow, is that positive? Is it negative? Is it neutral?
I don't know. It's kind of both, right?
Exactly. It's ambiguous. And if I'm the one labeling it today, I might mark it as negative because I personally hate slow shipping. I'm an impatient person, so slow shipping ruins the whole experience for me. But if you were labeling it tomorrow, you might mark it positive because you think, well, the product itself is the important part, and they said it was great. Now we have 2 completely different labels for the exact same type of sentiment in our data set. The model gets completely confused. It sees the same sentence structure labeled 2 different ways.
It's sending mixed signals to the AI. It won't know what the pattern is.
Exactly. So the project manager must work with the team to write down strict criteria. You document a rule. If a review contains both product praise and shipping complaints, label it as mixed. Or maybe the business rule is, Prioritize the product feedback over the shipping feedback and label it positive. You have to create the rule book. You essentially need a labeling Bible.
So that everyone on the team is singing from the exact same sheet of music.
Yes. Which leads directly to step 3, consistency controls. Because writing the rules isn't enough, you have to measure if the human labelers are actually following those rules consistently. We call this metric inter-annotator agreement.
How do you measure that?
You give the exact same set of, say, 100 reviews to 2 different labelers. They label them completely separately in separate rooms without talking to each other. Then you compare their work. Do they agree on the labels 95% of the time? Great. Your instructions are clear and the task is well defined. But what if they only agree 60% of the time? You have a massive problem. Either your criteria aren't clear enough, or the task itself is just too subjective for an AI to learn reliably.
I see. So you are rigorously testing the human labelers before you blindly trust the labels they are creating for the machine.
You have to. And this brings us to a very dangerous pitfall, the ad hoc trap.
I assume that just means the, hey, we'll figure it out as we go along approach.
Yes, the we'll just fix it in post mentality. This is a massive, incredibly common failure mode in AI projects. I have seen so many projects where a stressed out manager hands a massive pile of data to some summer interns or junior staff and just casually says, hey, go tag these emails as spam or not spam. No criteria document, no formal training, just some brief verbal guidance.
And I'm guessing the end result is a complete mess.
It's actually worse than a mess. It's systematically biased. The model ends up learning the individual labeler's implicit, unspoken biases. Let's say one intern thinks any email containing the word free is automatically spam, but another intern thinks free is perfectly fine if the email comes from a known brand name.
So the model's just going to learn this weird schizophrenic logic.
Exactly. It learns a disjointed logic that just reflects the confusion of the interns. And here's the real nightmare. When you try to debug the model's performance in Phase V, you won't find a bug in the Python code. You'll be staring at the algorithm thinking, why on earth does it predict this? You'll be chasing ghosts because the error isn't in the code. It is baked fundamentally into the model's understanding of the world, courtesy of those ad hoc labels.
That is genuinely terrifying from a project management perspective. It really emphasizes why this task is rated critical. You are effectively writing the brain of the AI right here in this step.
You are. In a very real sense, the data is the code.
Okay, what about reusing old labels? Say the company did a similar project 3 years ago, and we have a huge database of beautifully labeled data sitting around. Can we just use that? Waste not, want not, right? It saves time and budget.
You have just walked into the legacy labels trap. It is so tempting. It saves money, it saves time, but it is incredibly dangerous.
Yeah.
Just because a piece of data has a neat little tag on it doesn't mean it matches this new project's specific cognitive requirements.
Really? Why not? A label is a label.
Let's go back to the sentiment analysis example. Maybe the old project from 3 years ago only used a binary schema, positive and negative. That was all they needed back then. But your new project, based on the requirements you gathered in Phase I, desperately needs neutral and mixed categories as well.
Oh, I see where this is going.
If you feed that old legacy data in just to save time, the model will literally never learn to identify a neutral review because it was never taught that the concept of neutral even exists in the universe.
Huh.
It will forcefully shove every single nuanced review into either the positive or negative bucket.
So you're basically using an outdated map for a city that has completely changed its road layout.
Exactly. Or a map that doesn't even show the specific street you are currently looking for. You must strictly verify compatibility. You have to go all the way back to the requirements defined in Phase I and ask, do these old labels confidently answer the specific question we are asking the AI today? If not, you have to bite the bullet and relabel, or at the very least, augment the existing labels.
It really sounds like there are absolutely no shortcuts in Phase 3.
There are very few. And the ones that look like shortcuts usually lead you straight off a cliff.
So we have thoroughly covered the 3 groups: selection, cleansing and enhancement, and labeling. When we finally wrap up all the tasks in Phase 3, what do we actually have sitting in front of us?
We have a data set, but not just any data set. We have a verified ground truth. We have data that is carefully scoped, meaning we know exactly why every row is in there. It is cleaned, meaning we know it's valid and semantically correct. It's augmented, so we filled the coverage gaps. And it is accurately, consistently labeled, meaning we've formally taught it the logic of our business problem.
And this output is the direct, necessary input for Phase 3 model development.
Exactly. If phase 3 is weak, phase 3 will undoubtedly fail. People always say garbage in, garbage out. But in AI, it's more insidious than that. It's more like bias in, bias out, or
Sure.
confusion in, confusion out.
Before we close out this deep dive, I want to touch on one sort of big picture point from the outline. It's the EKO alignment, the examination content outline regarding pipeline design. This feels a little bit more technical than the rest of what we discussed, but the framework mentions it's highly important for a CPM AI practitioner to grasp.
It is, and it's vital for the project manager to understand this to avoid catastrophic architectural failures later on. The EKO highlights the critical distinction between training pipelines and inference pipelines.
Okay, what's the difference?
Everything we just discussed today, the cleaning, the augmenting, the careful labeling, all of that, is part of the training pipeline. This is often done in batch processing. You have a big, static historical file. You process it overnight on a huge cloud server. Time isn't really your main constraint. Accuracy is the primary goal. You take your time to get the data absolutely perfect for the model to learn from.
Right. You have the luxury of time to get it right in the lab.
But, and here's the kicker, how will the model actually be used in the real world once it's deployed? That is the inference pipeline, the live environment.
Well, if it's that credit card fraud detection system we've talked about before, it needs to work practically instantly. When I swipe my card at the grocery store, I can't stand there and wait overnight for a batch server to give me an answer.
Right. It has to be real time, streaming data. Sub-second latency.
So here's the massive trap that catches so many teams. If your data prep in Phase 3 relies on a complex step that takes 24 hours to run, like, say, waiting for a massive daily batch update from a legacy mainframe system, or worse, requiring a manual human review step before the data is clean but your live model needs to make a decision in 50 milliseconds, you have a fatal pipeline mismatch.
Oh, wow.
You prepared the data one specific way for training, using slow, rich, heavily processed data, but you physically cannot deliver that exact same quality and format of data fast enough for inference when the live model needs it.
So you essentially build a high-performance sports car that runs on a totally theoretical fuel that doesn't actually exist at any normal gas station. That is the perfect analogy. You trained it on high-octane slow fuel, but the real-world production environment only provides low-octane fast fuel. When it goes live, the model will choke and fail. Recognizing this mismatch, training versus inference, is a critical pipeline design gap that a CPM AI project manager must watch for during data prep.
So you have to be asking the engineering team, can we actually generate this exact data in this exact format in real time in the production environment?
Yes. And if the answer is no, you simply cannot use that feature for training, or you have to completely redesign your backend infrastructure before you move forward.
That is a huge gotcha. It really bridges the gap between the pristine world of data science and the messy reality of data engineering.
It does. And it is exactly why data prep is not just about the data itself. It's about the entire technical architecture.
Well, we've unpacked a truly massive amount of information today. It is crystal clear that Phase 3 is not just the janitorial work of AI. It is the solid foundation. It is the blueprint finally coming to life.
It absolutely is the foundation. Without this phase being executed correctly, the rest of the project is just expensive noise.
I always like to end our deep dives with a provocative thought to mull over. Something for you, the listener, to take with you. What is your final word on data preparation?
I would leave you with a fundamental mindset shift. Stop thinking of data preparation as just a setup task. In the world of AI, data engineering is software engineering.
I really like that.
Think about it. When you make the decision to exclude those legacy records back in Task Group 1, you didn't just filter a spreadsheet. You wrote a business rule. When you decided how to explicitly define positive sentiment versus mixed sentiment in Task Group 3, you essentially wrote a logic gate. The decisions made here in Phase 3, what to exclude, how to augment, how to meticulously label, these are the hard-coded rules of your future AI system. You weren't just prepping data, you were literally programming the fundamental behavior of the AI. You have to treat these data decisions with the exact same rigor, review, and respect that you would treat a line of critical software code.
Data engineering is software engineering. That is a truly powerful takeaway. It gives this entire phase the weight and respect it deserves. Thank you so much for guiding us through the weeds today. This has been incredibly clarifying.
My pleasure. Like I said, it is arguably the most important phase to get right.
And thank you to you, our listeners, for diving deep with us. Phase 3 is officially in the books. Next time, we take this shiny, clean, perfectly labeled fuel and we finally pour it into the engine. We'll be tackling Phase 4, model development. You definitely won't want to miss it. Until then, keep asking the hard questions about your data.
And please verify your labels.
See you next time.